Hello and welcome back. So far we have covered lots of linear algebra, including vector algebra also, and we have understood what is eigenvectors and eigenvalues also. Let us try to understand what is singular value decomposition, a very important linear algebraic concept used in many areas in machine learning. So singular value decomposition can be called as a more generalization of eigenvalue decomposition, because eigenvalue decomposition can be done on a square matrix only, but singular value decomposition can be done on any matrix. If you see this, singular value decomposition can decompose an m by n matrix where m is not equal to n, right? And this is more generalization of eigenvalue decomposition only. We'll see it in a moment. When you see the actual math, right, you will understand what I'm actually saying, what I'm actually talking about. Singular value decomposition provides a way to factorize matrices into singular vectors and singular values. The SVD allows us to discover same kind of information as eigen decomposition. What are you finding in eigen decomposition? When you decompose a matrix into eigenvalues and eigenvectors give you the essence from data, eigenvalues give you each vector how much essence it is extracting. Eigenvectors and values are in pairs. First vector and the first value will give you, it's a pair. First vector will extract some essence from data, how much quantity it extracted. The first vector, first value will tell you. And second vector and second value. Second vector, how much essence it extracted, second value will tell. Similarly here also, eigenvectors will extract the essence from data and eigenvalues will tell you how much each vector extracted the essence from the original data. Okay, and this can be applied on a non-square matrix also. Okay, so it is more generalized and more useful. However, the SVD more generally applied, even every real matrix has a singular value decomposition, but same is not true with eigenvalue decomposition. So scientists, the mathematicians have more generalized eigenvalue eigenvectors and created singular value decomposition. That's it. It is a simple thing. If you see this, right, in a moment you will understand. So matrix C can be decomposed into U sigma V transpose. This is called as singular value decomposition, where U and V are orthogonal matrices. What is orthogonal matrix? I'll explain in a moment. U and V are orthogonal matrices, and sigma is a diagonal matrix. When I say diagonal matrix, only diagonal values will be there and half diagonal values are all going to be 0. Upper triangular, lower triangular are going to be 0. Of the square root of the eigenvalues matrix is nothing but the sigma. Square root of the eigenvalues matrix is the sigma. U and V are the orthogonal matrices. First, let us see what are orthogonal matrices and what is inner product. When you understand orthogonal matrices, orthogonal vectors and inner product, right, it becomes easy to understand singular value decomposition. Let us see what is that. So orthogonal vectors and orthogonal matrices. If two vectors U and V are orthogonal, we will say if two vectors are orthogonal only when they are perpendicular to each other. They are like this. When they are perpendicular to each other, right, when you multiply one vector with other, you will get 0. We have seen that when you multiply two vectors, you will always get a scalar, right? So when two orthogonal vectors are multiplied, you will get 0. So when two vectors are perpendicular to each other, right, we call them as orthogonal vectors. If one matrix contains all columns orthogonal to each other, then that matrix is called as orthogonal matrix. You see this? U inverse is equal to U transpose. Or when you multiply a transpose, when you convert rows into columns and keep your original matrix and multiply each other, which is nothing but vector multiplication, right? You get I. It means diagonal values you will get 1 and half diagonal values you will get 0, because multiplying one vector with itself, the orthogonal vector unit vector with itself, you will get 1 and the half diagonal values you will get 0, right? So because one vector is orthogonal to other vector, when you multiply those two vectors, one column multiplied with other column, you get 0. So that's where when you multiply U transpose with U or U inverse, any matrix inverse itself is I, right? So when a matrix is orthogonal, if you multiply its transpose or inverse, it is equal, because inverse is equal to transpose. Okay. So orthogonal matrix, we say the matrix contains all orthogonal vectors, then you call it as orthogonal matrix. Then inner product. Let us try to understand what is inner product. U transpose U is the inner product. If you take a matrix U and you are trying to transpose it and multiply it with itself, it is called as inner product. When you transpose a matrix, what are you trying to do? You are trying to make columns as rows, right? You took the column matrix as first one and original row matrix as second one, and you are trying to multiply this with this, right? So what happens? You are going to get a relationship between each column and its the other columns. Okay, the inner product gives you the correlation matrix between the features and the features, all the features. So the columns are mutually orthogonal if and only if U transpose U gives you a diagonal matrix. Okay, and the columns are linearly independent if and only if U transpose U gives you singular matrix. If the columns are linearly dependent, right, then you get a singular matrix, because we have seen that in our normal equation based approach in linear regression, when you have strongly correlated columns or dependent columns, when you try to do x transpose x, what you are getting? You are getting a singular matrix. When you have strongly correlated or dependent vectors in your matrix, you try to transpose it and multiply with itself, you will get a singular matrix. If the columns are orthogonal, then you will get a diagonal matrix. Diagonal values will be there. If the vectors are unit vectors, you will get identity matrix. If the vectors are not unit vectors, then you will get some values in the diagonal. Off diagonal values are going to be 0, because one vector, one column is orthogonal to other column. When you multiply two columns, you will get 0. So that's where you get a diagonal matrix. The values of ij index in U transpose U, right? In U transpose U means you are multiplying columns with columns. First column with first column, first column with second column, first column with fourth column. So again, second column with first column. It's a matrix multiplication, right? So when you do that, right, the ij index gives you the correlation between feature I and feature j. Ij index value, the cell ij contains the correlation between the feature I and feature j. Okay, so the higher the value, the correlation is higher. I gives you the correlation between the feature and itself. It is going to be high, right? So those are the orthogonal vectors and orthogonal matrices. In simple words, if two vectors are perpendicular to each other, then we call them as orthogonal vectors. If a matrix contains vectors which are all orthogonal to each other, then that matrix is called as orthogonal matrix. When you decompose a matrix into U sigma V transpose, you get two orthogonal matrices, UV and a sigma, which is nothing but the eigenvectors, eigenvalue square root. Let us see how and why it is. If you look at singular value decomposition, in a simple words, if I have to say, to find out the V vector, you need to find the eigenvalues and eigenvectors for C transpose C. Your C is the original matrix and you are trying to decompose it into U sigma V transpose. To find out V, you need to calculate eigenvalues, eigenvectors to C transpose C. To find out U, you need to find out eigenvalues, eigenvectors to C transpose. What are you doing here? It's a non-square matrix and you took it. When you do C transpose C, you get a square matrix. C transpose also you will get a square matrix. You are trying to decompose it using eigenvalues and eigenvectors only. Ultimately, you are using eigenvalues, eigenvectors only for SVD also. Let us try to understand this clearly in another session. Thank you.